I'm going to be telling you about experiments we're doing at Princeton with quantum simulations using fermionic atoms and optical lattices. And basically the overarching theme of the research we do in my group is to use quantum simulators to try to understand strongly correlated quantum systems. And of course, these occur all over the place in condensed matter. These are materials where the electrons are interacting strongly with each other. And this gives rise to some interesting emergent properties. So for example, examples of such materials include like high temperature superconductors or fractional quantum Hall systems or heavy fermions. And of course, we're interested in eventually making use of the exotic properties of these materials for technological applications. But to get there, we need to understand the basic physics of these materials, preferably on a microscopic level. So that's where the quantum simulators that I'm going to talk about come in handy. So let's understand why this is a very difficult problem. So here's an example of a high temperature superconductor. You can see under the hood, it's a very complicated material. It has a complicated chemical composition. There's a lot going on, and trying to do an ab initio simulation of everything that's going on in here is almost definitely impossible with today's technology, with classical computers. So what condensed matter theorists do when they try to understand such materials is they come up with a simplified description. And of course, when you try to simplify the description, things can go wrong there if you don't capture the essential physics of the material. But let's say that step went correctly, and now you have a simplified model of what's going on in this high temperature superconductor. For example, a common model I'll talk about today is this Hubbard model that was introduced by Princeton physics Nobel laureate Phil Anderson a long time ago. So now you have this Hubbard model, and you would like to try to understand what's going on in it. For example, what's the phase diagram, or you'd like to compute some dynamical properties like resistivity, for example. So even that step is also very hard because, as you know, trying to simulate a quantum system requires exponential resources in time and memory. So there was a clever solution that was proposed a long time ago. Instead of trying to do the simulation on a classical computer, it's probably better to use another quantum system to do the simulation. This was an idea that goes back to Richard Feynman. So he said, you can take a very well-controlled and flexible, versatile quantum system and use it as a simulator to simulate the physics of the original system. And people have been trying to build these quantum simulators out of different systems like atoms or photons or molecules and so on. So you can think of them basically as tailor-made quantum computers. They're not quantum computers that are universal or gate-based. They're quantum computers that are analog, and they're tailored to solve certain classes of systems. And because they're tailor-made computers, if you're trying to solve different problems, you need different types of quantum simulators. So in my group, we're trying to tackle a broad set of problems. So we're building we build different kinds of quantum simulators. One of them, the one I'm going to focus on today, is these cold atoms and optical lattices. They naturalize these Hubbard models that I was just talking about for high temperature superconductors. So these are basically, you have lattice fermions with purely on-site interactions in the optical lattice. Another kind of system that we also work with, and I know, for example, Luigi is interested in, is these Rydberg atom systems. So there you can either have the Rydberg atoms frozen on sites, and there you can simulate things like quantum Ising spin models, or you can have them hop around and simulate lattice fermions with off-site interactions. And a third system we have is polar molecules in optical lattices, where the polar molecules interact with each other through their electric dipoles and can realize things like anisotropic Heisenberg models or dipolar Bose gases. So the common theme throughout all the work we do is a technique that we developed back when I was a PhD student at Harvard that's called quantum gas microscopy. So this is a technique that allows us to probe and manipulate the individual particles in these systems at the single site level. Okay, so I'm going to focus on the first of these systems in this talk, the ultra-cold fermions and optical lattices, and tell you a story about how we're trying to understand the phase diagram of the Fermi-Hubbard model using that system. So when I say ultra-cold atoms, what do I mean? So these are basically very dilute vapors that are isolated in a vacuum chamber. They're trapped. The typical spacing between the particles is about a micron or so. We typically use alkali atoms because they're easy to laser cool. They're very cold, so you can see here on this logarithmic temperature scale, this would be here room temperature. And I'm talking about temperatures that are about 12 orders of magnitude lower. So we're talking about temperatures typically in the microkelvin to nanokelvin regime. That's where we do the physics. And the reason we have to be so cold is that the gases we're working with are very dilute. We need to work with dilute gases because if we make the gases denser, then you wouldn't just have elastic collisions between the particles. Sometimes you would have inelastic collisions, and then you would start to lose the atoms. Now, of course, when you're restricted to working with such dilute gases, if you're interested in reaching the quantum regime, you have to be very cold. Because you remember, to be in the quantum regime, you want to have the thermal de Broglie wavelength of the atoms be comparable to the interparticle spacing. So you need to lower the temperature. And since the atoms are really heavy compared to electrons in a solid, you need to, and they're spaced by such far distances, you have to cool them much more to enter quantum degeneracy. So we need to cool down to about a microkelvin in order to study, for example, if they're bosons, Bose-Einstein condensates, or if they're fermions, degenerate Fermi gases. And of course, you can't use cryogens to get that cold. You have to use some different cooling techniques. And fortunately, in atomic physics, we've had decades of work on this topic that has been awarded several Nobel Prizes. You can see here the gentlemen who have received these. So they've developed over the years these techniques which allow us to use laser cooling to get very cold, down to the microkelvin regime typically, hundreds of microkelvin. And then we have another technique called evaporative cooling that allows us to get even colder down to the nanokelvin regime. So what you're seeing in this picture here is, it's a cell phone picture actually, taken of a cloud of lithium atoms trapped in a vacuum chamber in my lab. So this is about 1 billion atoms roughly. So not that many atoms, but they still glow so brightly because the lasers that are scattering light off them are resonant. So they're scattering so much light that you can just see it with your bare eyes, and lithium scatters in the red at 671 nanometers. So you can just see it really. And the typical size here is about a few millimeters of this cloud. So within a few milliseconds, you can bring down the temperature of the atoms from above room temperature. You typically have to heat up this alkali atom maybe to 400, like to several hundred degrees, and then cool it down to a temperature of below a millikelvin with lasers. There's a limit to laser cooling because when you're scattering photons of the atoms, they're always jiggling around. So they have some temperature. But if you want to get even colder, then you want to trap them in the dark. So here in this configuration, they're trapped in what's called a magneto-optical trap. We're using a combination of magnetic fields and lasers to trap them. But if you want to get colder, you trap them in something called an optical dipole trap. So you basically focus a laser beam onto the atoms. And it's very similar to the optical tweezers people use, for example, in biology. These are just very far off resonant laser beams, which can hold the atoms without scattering photons. They're just conservative forces. And once you have the atoms in this sort of trap, you can spill out the hot atoms, and the remaining ones thermalize to a lower temperature. So it's an evaporative cooling process, very similar to how, say, your coffee cools down. And at the end of this process, we can achieve quantum degeneracy. So what happens there, it depends on whether your atoms are bosonic or fermionic. And for the lithium isotope we're using, lithium-6, it has 3 protons, 3 electrons, 3 neutrons, so a total of 9 fundamental particles. So it's a fermion. Lithium-7 has 1 extra neutron, it would be a boson. So if you're working with lithium-6, you end up with a degenerate Fermi gas. If you're working with lithium-7, you end up with a Bose-Einstein condensate. So here I'm going to focus on lithium-6. So we're going to be working with Fermi gases, and that's nice because the electrons in a solid, which we're trying to simulate, are fermions. Okay, so now we'd like to make this degenerate Fermi gas look even more like a solid. And in a solid, one of the characteristic things you have is a band structure, because you have an ionic crystal, a periodic potential, basically, in which the electrons move around, and that gives rise to the band structure. So to give our atoms a band structure, so now basically the atoms are playing the role of the electrons. So we want something to play the role of the ionic crystal. And the way we do that is something called an optical lattice. So we take laser beams and make them interfere with each other, and they create standing waves of light. And the atoms experience this modulated intensity pattern of the light as an effective potential through the AC Stark effect. So the atoms move around in this periodic potential, and now they have a band structure. And the typical spacings here we're talking about are, their interference of light. You get micron level spacings as opposed to the angstrom level spacings in a solid. So this is really a hugely enlarged model for condensed matter physics, about 4 orders of magnitude larger than what you have in a condensed matter system. So why would you want to work with such a quantum simulator? First, we understand really everything about the system from first principles. So unlike in a condensed matter system where when you write down a Hamiltonian, you just basically have a very crude approximation of what's going on. Here, we really understand everything that's going on. So the Hamiltonian we write down is almost exact. If we have any approximations, we completely understand them. And furthermore, we have complete control over the parameters of this Hamiltonian. So we can tune things like, say, you'd like to tune the tunneling between the sites in this potential. You can simply change the laser intensity, and it will change the well depth. We have knobs to change the interactions between the atoms. We can change, as I said, the species. We can change the geometry of the lattice, so we can work, say, with a square lattice or a triangular or whatever interesting lattice you want to work with. So you can think of it basically as if you have Lego blocks with which you can build up a quantum many-body system. And these are very clean systems that don't have impurities. But if you're interested in studying disorder physics, for example, you can add that in a controlled way. So the fact that we're using atoms rather than electrons, so they're much heavier and the spacings are much larger, means the dynamics are very slow. So they're typically milliseconds rather than femtoseconds in a solid. And it's also, this large spacing is very important for the technique I was telling you, this quantum gas microscopy. It means that we can actually go and probe and manipulate the system down to the single site level, just using normal visible light or near infrared light, instead of having to use, say, an STM. Okay, so here's a picture that we take with such a quantum gas microscope. So each one of these dots here is a single atom. So of course, an atom is like angstrom scale, but what you're seeing here is basically the point spread function of the atom on a camera. So that's on the scale of half a micron or so. And that's very comparable to the spacing in the lattice. So basically the particles are barely resolved, but we can still tell which site has a particle, which site doesn't have a particle. And I want to remind you here that basically before taking this image, you really had a quantum system. So it had, the particles were tunneling around, they were interacting strongly. So there was all sorts of quantum many-body entanglement in the system. And then when you would take such a picture, you project this quantum many-body wave function onto a particular realization in density and spin. And now you're able to extract all sorts of correlations and fluctuations that are existing in the quantum many-body system. So the way we take these pictures is, of course, you want to scatter some light. Typically, you want to scatter about 1,000 photons per atom to get a sufficient signal to noise on the camera. So what we do is we first very quickly freeze the tunneling by increasing the depth of the lattice by a factor of 1,000 or so. So now the tunneling is completely frozen. We've projected the system onto a particular realization. And then we can scatter some light. It turns out the light heats up the atoms quite a bit. So under normal circumstances, we get a picture like this, where the atoms have now heated up so much that they can start to thermally, just classically hop around the lattice, as you see in this movie. But of course, that's not what we want. So this is just showing you a video for fun here. But what we want is to get an accurate representation of which atoms have which sites have atoms and which don't. So there, we actually shine the light in a laser cooling configuration where the atoms are starting from near zero temperature, then they heat up because of the scattering, but eventually, because of the laser cooling power, they reach some equilibrium temperature, which is well below the lattice depth. And so we can reconstruct a faithful representation of the density and the spin in the system. Okay, so maybe I'll pause here and ask if you have any questions about the technique or the big picture. Okay, go.
Yes, Alan has a question. Wait, there is a question.
Hello, hello.
Please.
Can you hear me?
Oh, yes.
So I'm interested. So you say you can control the atoms in the single site level, right?
Yeah.
So you basically, like, if you want to simulate only a two-site interaction, you can do it without disturbing the rest of the system, or not?
I mean, there are techniques that you want to control the interaction on two sites.
Yes,
so
just two
yeah,
sites.
I mean, so there are. I mean, the thing that gives us really access to single sites is optics. So you can focus laser beams down on the single site level, and there are techniques that are called the Fetchbox Resonance, which allows you to tune the interactions between the atoms. Typically, people use something called a magnetic Fetchbox Resonance, where you can tune the interactions globally with a magnetic field. But there's also techniques called optical Fetchbox Resonance, where you can do this tuning with lasers. And there, if you kind of focus down on say on single site or pair of sites, then you can do a local change of the interactions. You can also tune, say, the barrier between two sites, and then you can have the atoms, say, in a controlled way, undergo a collision between these, the atoms on these two sites can undergo a collision. So you can do things like, say, realize a collision-based gate, for example, if you're thinking of quantum computing.
Things in terms like a fermionic beam splitter, something like this.
Mm-hmm. Yeah.
Okay. Okay, thank you.
There is another question by Rene. Please, Rene, go ahead.
Sure.
Thank you, Alan.
Yeah. Hey, so far, really very, very clear. Thanks a lot. I remember, Waseem, that there is this, when you image atoms in the lattice, there is this issue with this, I think it's called light-assisted collisions,
yes.
that if you have two atoms on one side, that you would then kick them out, or more like odd and even number detection. So is this also the case here? Or
yeah, in this picture here, and actually throughout the pictures I'm going to show you in my talk, that's going to be I call this like a conventional quantum gas microscope. You would have these light-assisted collisions. So the process is what you described. You shine some photons, and then the atoms kind of switch. One of them goes from an S to a P. The other one, let's say, stays in an S. And so suddenly the potential between them changes from a van der Waals 1/r⁶ to a 1/r³. And so they get suddenly much stronger. And so they experience this force that brings them together. And then they gain so much energy that they get ejected, this pair of atoms, immediately from the site. And so the measurement is typically the atom number modulo 2. So if you had like 3 atoms, two of them would undergo such a light-assisted collision, and you would be left with 1 atom. So there are techniques now that circumvent this. So, for example, in my lab and in at MPQ, what they do is we split this layer. So typically I'm working with a two-dimensional layer for microscopy, but you can split it, say, out of the plane. And in the Fermi-Hubbard model I'll be describing, you can at most have 2 atoms per site. So then you would, say, get the spin-ups in one layer, the spin-downs in a different layer, and then you can image those separately without having to worry about the light-assisted collisions. And then you can get the full density and spin information.
And how would you do the splitting? How does this work technically?
Technically, you apply a magnetic field gradient. So you have a Stern-Gerlach that the different spins have different magnetic moments, and so you split them using magnetic field gradient, and they end up in different layers of a lattice that's in the third direction. That's the one that's in and out of the plane. And then since they're on different sites, there's just 1 atom per site, and you just have the light-assisted collisions. And then if you've separated them sufficiently far, let's say like 20 layers or so, then they are in different foci on the camera. So you can focus on the different layers, let's say with optics, simultaneously on different regions of the camera, and you can get the two pictures of the 2 layers.
Super, thanks.
Thank you very much, guys, for the questions. Thanks, Waseem, for the presentation and the didactic. It's very pedagogical. Thank you so much. Please go ahead. Thanks.
Okay, so yeah, so now you could ask, what sort of physics can we study with this system? And the natural physics that comes out is this Fermi-Hubbard model that describes a lot of correlated materials, most famously the high temperature superconductors, but there are many other correlated materials like the pnictides, for example, or others that you can study with this Hamiltonian, with this type of Hamiltonian. So this is a Hamiltonian that has had decades of work on it ever since Phil Anderson first suggested it might be used to understand the cuprates. There's a lot of theory work, and we still don't understand the low temperature phases of this Hamiltonian. So I'm not claiming this Hamiltonian describes the cuprates exactly. As I said, in a condensed matter system, things are complicated, but this is what we believe to be a minimal description of what might be going on in these systems. And of course, so it's one of the things we can study with this microscope. If you start adding lasers in different configurations and so on, you can extend this Hamiltonian to study different physics, but this is maybe the sort of the prototypical physics you can study with this, the class of physics you can study with this particular quantum simulator. Okay, so let me explain what the Hamiltonian is here. So we have fermions in a lattice. We're gonna, for concreteness, work with a square lattice, just like the cuprates. And we're gonna work with 2 species of fermions, because the electrons in a solid, you have 2 spin states up and down. So here, similarly, we're going to prepare the atoms in one of 2 hyperfine states. So we're going to have 2 hyperfine states that are metastable. They're going to be very long-lived over the time scale of the experiment. And we're going to call these pseudospins up and down in analogy to the states of the electrons in a solid. And the fermions can do one of 2 things. So the first term is a hopping term. They can hop around between neighboring sites. So I and J are site indices, and we're just hopping between neighboring sites. And the sigma index here is a spin index. So the hopping preserves the spin. In this case, you're destroying a fermion on site J and creating another one on site I, or the opposite process, with a matrix element T. The other process you can have is you can have 2 fermions land on the same site, and then they can interact strongly with an interaction of strength U. So this is the density here operator. So if you have an atom, a spin up and a spin down on the same site, there's a shift in the energy by U that is typically repulsive. So it increases the energy. We can only have opposite spins land on the same site because of Pauli blocking. So we're working with a single band model here. If you're working with a multi-band model, you can have 2 spins on the same side that are the same, but we're just going to work at temperatures low enough that you only have a single band of the Hubbard model occupied. And we can tune all the parameters of this Hamiltonian. So you can tune the interactions using these Fetchbox resonances I mentioned. You can tune the tunneling by changing the well depth, the laser intensity essentially. You can tune the number of atoms in the lattice to tune the chemical potential. You can tune the temperature of the system in a controlled heating. So you can essentially try to explore the full phase diagram of this Hubbard model. And the question we're posing is how much of the phenomenology of the cuprates does this model reproduce? So so I can't show you a phase diagram, a theoretical phase diagram of the Hubbard model because we still don't know one, okay? But what I can show you is an experimentally measured phase diagram of the cuprates. And if we believe the Hubbard model describes the cuprates, then it would probably have a very similar phase diagram. And the phase diagram you're seeing here is in terms of the temperature and the doping. So the temperature is self-explanatory. Doping, I'll explain. So we call a system undoped if you have an equal number of fermions and lattice sites on the average. So you don't have to have one fermion per site, but on the average, they're equal to each other. So say 10 fermions, 10 sites. And then if you remove some particles from the system, you are whole doping it. Or if you add some more particles, you're particle doping it. So the cuprates can be studied in the undoped regime, which sometimes people call half filling because the sites are filled with, on average, with one fermion per site. So that's half the maximum you could have if you had an up and a down on each site, in which case you would get a band insulator. So at half filling, the cuprates are at a strong interaction. So U/T typically about 8 or so. And for this strong interaction, it turns out the atoms or the electrons in a cuprate want to arrange themselves so that you have one electron per site, because this second term is dominating at strong interactions, and that just penalizes having 2 fermions on the same site. So we're going to end up, if you have an equal number of fermions and sites in the undoped system, 1 fermion per site, and that's what's called a Mott insulator. So in the limit of very large interactions, you have a Mott insulator. If you start to introduce a little bit of tunneling, then you have quantum fluctuations on top of the Mott insulator. So you can have tunneling between, let's say you have 1 atom on every site, and then you have an atom hop over to a neighboring site, creating a doublon, and then next to a hole and hop back. Okay, so this is a sort of the elementary quantum fluctuation in the Mott insulator. Then if you lower the temperature further, you get into what's known as an anti-ferromagnet. So basically the spins start to order, not just the density, but the spins start to order. So there the system is described by a Heisenberg model. So you imagine you have 1 atom per site and they have a spin, and there's a super exchange process where the spins want to anti-align with each other. And so you get an anti-ferromagnet, and this anti-alignment can happen anywhere in any direction. The Néel order parameter can point in any direction on the Bloch sphere. So these 2 phases, the Mott insulator and the anti-ferromagnet, are well understood in the Hubbard model because we can do simulations in the undoped systems in a numerically efficient manner. So the gold standard there is something called quantum Monte Carlo. And with quantum Monte Carlo, there is no fermion sign problem in undoped systems, which means that you can go to low temperatures and you don't run into issues with the numerics being hard. But then once you start to dope the system, the numerics get really hard. But that's really where the interesting physics is in the cuprates. So at low temperatures, you have the D-wave superconductor, and then that's what's shown here. But even in the normal phase, there's a lot of things going on. Here, I'm just showing a very simplified phase diagram. The most famous phases are this strange metal, where you have anomalous transport properties, and the pseudogap, where you have basically a gap opening up in the system below a temperature scale T star, even before the system becomes superconducting. And that's very unusual because typically in superconductors that we understand, conventional superconductors, BCS superconductors, there the gap opens once the system is superconducting. But here you have a gap even before that. So these are the phases we would like to understand, this normal state, because people think that if you understand what's going on in here, then you can understand the pairing glue will eventually lead to the condensation in the superconducting phase. Yeah, go ahead.
Yes, yes. Strange metal. So anomalous transport. Do you mean non-Fermi liquid behavior like resistivity that doesn't depend on the square?
Yeah, I'm actually going to spend quite a bit of time on that, and yes, that's one of the signatures as resistivity.
Okay, so it's non-Fermi with you. Okay, thank you.
Yeah, yeah, and this here is a Fermi liquid, this yellow region here.
Okay, thank you.
Okay, so let me show you first maybe some of the easy phases.
Can I add a little question, very basic one in my case? Yeah. So what exactly is it not understood then? So I've been hearing this story that the phase diagram of the Fermi-Hubbard model is like the gold standard goal of quantum computing, because you could understand something. But so from what you described here, like what is it that is not really understood?
I mean, this is an experimentally phased diagram where the experimentalists measure properties of the system, like resistivity in the case of the strange metal, and they find a strange behavior, which is resistivity that goes linearly with temperature. The pseudogap phase, again, there's a behavior in the gap that we don't understand. But the microscopics of what causes these behaviors, in particular, what is the glue, that pairs the fermions in order for them to condense into a superconductor, that's what we don't understand. So in the case of BCS conventional superconductors, Bardeen-Cooper-Schrieffer superconductors, there's been a theory, around for a very long time where we understand the pairing between, these electrons. They want to stay away from each other in principle, but there's the phonons that glue them together. So there we understand
so it's the pairing process, what is not really understood.
Yeah,
right?
the microscopics of what's going on and giving rise to these macroscopic phenomena. That's what we would love to understand, so that we can learn how to optimize the critical temperature and eventually reach a room temperature superconductor.
Okay, cool. Thank you. Yeah.
Okay, so let me show you some of maybe the easier to understand phases now in the experiment. So here's a picture of a Mott insulator. So in a solid, of course, the electron density is fixed. In our systems, we're putting atoms into laser beams that are forming the lattice, but these laser beams have a finite spatial extent. They're like Gaussian laser beams that we focus down. And so there is a variation of the intensity of the laser beam. And when you put the atoms in there, there's a lot of atoms in the center, and then towards the edge, there's no more fermions. So that means the electron density, the atom density is varying. And we can think of the system in what's known as a local density approximation. So you can just think of it as a lot of small homogeneous systems, each with a fixed local density. And so in this local density approximation, you can define a local chemical potential that is being scanned across the trap. And so we're really taking a cut through the phase diagram where we're looking at different dopings, if you will, in our system, where doping is like related to the particle number. So at the center of the trap, in this case, the chemical potential is appropriate for forming a Mott insulator, where you get one atom per site at strong interactions. And then towards the edge, you get into a metallic phase. So you can't see the one atom per site here because, as I said, the point spread function is very similar to the lattice spacing. So we can barely resolve the atoms. But if you can see maybe here in the picture, the missing atoms. So here's a missing atom, here's a missing atom, here's a missing atom, right? And if we take a picture of a dilute gas, then we can reconstruct the underlying lattice, make a grid and overlay it on top of our pictures. And then we can tell with high fidelity, over 99%, whether we have an atom on a site or not. Okay, so we have a Mott insulator in the center and then a metal on the edge. Now I could also change the chemical potential at the center by putting more atoms into this lattice, and then you get a picture like this. So now you see this light-assisted collision story that we were discussing earlier. So when we have the chemical potential in the center sufficiently large, then you form a band insulator, which has 2 particles per site, and a spin up and a spin down. So now you have an insulator due to the band gap rather than due to the interactions. And then when you shine light on this pair of atoms in the center, there's this light-assisted collisions, and the pair gets ejected, and you get an empty hole in the center where the band insulator used to live. There's like the atoms get kicked out in very quickly within a few photons, and the remaining 1,000 photons you need, they're not there, but they're just there on the edges where you have a Mott insulator. So in the middle, there's a band insulator, and that's surrounded by a Mott insulating shell. Okay. So of course, we can do all this stuff very quantitatively and compare to quantum Monte Carlo, look at the density versus temperature and so on. It all agrees very well. Okay, so let me show you one other phase. Let's look at the anti-ferromagnet. So we're going to go down in temperature now with the Mott insulator, and we're going to look at the anti-ferromagnet. And again, this is a conventional quantum gas microscope where it's hard to measure the spin. As I mentioned, there are techniques to measure the spin, but here we're just looking at one of the spin states. So what we do here is we use some resonant light to eject one of the spin states. So let's say we get rid of spin ups, and then we're just looking at the spin down atoms. So this is a picture of the spin down atoms. And before we ejected the spin downs, we had a Mott insulator in some region of the cloud, let's say over here. And then we had the metal towards the edges. But then once you've ejected the spin ups, you're just looking at the spin downs, you can see some interesting patterns. For example, in this little patch here, there's sites where it's empty, not empty, empty, not empty. So that's where you used to have a spin up, spin down, spin up, spin down, right? So that's the anti-ferromagnet. And you don't expect to see the anti-ferromagnet everywhere in the system because this is really a quantum anti-ferromagnet. So, your Néel order parameter, which way the spins point, can be anywhere in the Bloch sphere. So in some regions, it will happen to align with your imaging basis, and then you'll see a little patch of anti-ferromagnet like this. In other regions, it will be orthogonal to it, and then you'll just see some random distribution. And this is also there's not only quantum fluctuations in the system, there's also thermal fluctuations. So there's a finite correlation length for the system. And so you basically get these patches whose size is set by the temperature of the system, essentially. So if this is what a single snapshot looks like, but then you can take many of these snapshots, say 100 or so, and then extract from there a spin correlation function. So that's what you see on the right here. So basically, this is telling you if I had say, this is the central spin here. If I had another spin here, it's anti-aligned, while this diagonal spin is aligned in an anti-ferromagnet. So you can clearly extract from this kind of picture the correlation length. And by comparing to quantum Monte Carlo, you can now use the temperature as a free fit parameter and extract the temperature of this anti-ferromagnet. And then the prediction is what all the other spin correlations are. So this is basically our thermometer. Luigi, you have a question?
Yes, I have a question. So you were talking about quantum fluctuations and thermal fluctuations. So I imagine this picture come from a just given temperature, and then you and given interaction. Okay. Mm-hmm. Can you somehow make a separate study of the two quantities? So imagine you have you fix the temperature, you fix the interaction, and you change the temperature, you cool down, you cool down, you cool down to see the effect of, say, a situation in which you have more quantum fluctuations than thermal fluctuation, and vice versa. So can you do that?
Yes. I mean, we can cool down. Now, the question is, how cold can you get? So the lowest temperatures we can get are 0.3 of the tunneling. So about half of the super exchange. Okay, so it's not very cold compared to the super exchange, and that's why you're not seeing very long correlations. That's the record, I think, is about is roughly 0.2 times the tunneling. We usually measure the temperature units of the tunneling. So that's as close as you can get to just seeing mostly quantum fluctuations. And then as you can, in a controlled way, heat up the temperature, let's say by modulating the lattice depth, for example. You can pump some energy into the system, let it equilibrate, and then you can increase the temperature and you'll get more and more thermal fluctuations.
Okay, thank you.
Okay, so now I want to switch to this strange metal phase that Luigi was asking about earlier. What does it mean to be in a strange metal? So this anti-ferromagnet and the Mott Insulator, as I said, these we understand. We know everything about the quantum Monte Carlo we can do. But this is where the real questions are. Strange metal, pseudogap, that's where we don't understand much. Okay, so let me first define a strange metal by contrasting it with what a normal metal is. So a normal metal would be a metal where the interactions are weak, and we can describe the behavior of the system in terms of quasi-particles. So these quasi-particles are basically like dressed versions of the electrons, and they carry the various conserved quantities like charge or spin or energy. These are all carried by the quasi-particles. So the quasi-particles are just moving around, bouncing off each other, and they collide every mean free path, which I'm denoting as L. So we have a velocity v, which is on the order of the Fermi velocity for these particles. So there's a typical collision rate gamma between the particles. And you can relate this, if you remember, this gamma is like a momentum relaxation rate. So from freshman physics, we know we can relate this through the Drude model to a resistivity. Okay, so that's what's shown here, rho. And now we can set various limits in a normal metal, in a quasi-particle metal, on these quantities. So for example, let's imagine you start to heat up your metal. Then you know the resistivity increases. The mean free path gets shorter as you increase the temperature. And naturally, it cannot get shorter than the interparticle spacing. It just doesn't make sense to talk about something that's shorter than the interparticle spacing when you're talking about quasi-particles. Also, it cannot get shorter than the lattice spacing. So there's a minimum mean free path you can talk about. And that corresponds through these relations to a maximum resistivity you can reach. So if you take a quasi-particle system, you heat it up, then the resistivity will eventually saturate at some limit. And that's what's known as the Mott-Ioffe-Regel limit, this MIR limit, the maximum resistivity or minimum mean free path. Another aspect of the resistivity that you can also measure is how it depends on temperature at low temperatures. So there are many different sources of resistivity in a material system. So you can have disorder, you can have phonons, the electrons are scattering of the phonons, or the electrons can scatter off each other. So the interactions between the electrons. And each of these, if you look at it through Fermi liquid theory and Boltzmann theory, they lead to a different dependence on the temperature. So in particular, the interactions, they lead to a t-squared dependence on the temperature. So usually in a real system, you have all these mechanisms acting, but in our systems, we actually only have the interactions because our lattice is rigid. It's just made through this light. We don't have like in an ionic lattice, the atoms can move around. But here we just have a rigid potential through the optical lattice. So we don't have any phonons in our system. And we also don't have disorder because it's a clean system. So the only source of resistivity is just this interactions, which should lead to a t-squared behavior in a quasi-particle regime. Now, if you go to a strongly interacting system, you destroy these quasi-particles. And there, the resistivity has some strange properties. So for example, you find that it no longer saturates at this MIR bound. If you increase the temperature, it just keeps going up. So that's something people don't understand so well. And another thing that you find in a lot of these materials like the cuprates and so on, is the resistivity often goes linearly with T. So this is something you expect from phonons, but you don't expect from interactions. The interactions should lead to a t-squared behavior. So it's not clear in the cuprates what's causing the linear in T behavior. People think the phonons shouldn't be playing a role, but sort of disentangling this role of phonons interactions is a mess. And that's where we hope our quantum simulators can be helpful. So we have a clean realization of just pure interactions. And the question we posed in this study is, what sort of behavior do we have for the resistivity? Can we get this linear in T behavior in the Hubbard model? And surprisingly, this question is, people started to explore it a little bit a long time ago, but then the numerics weren't good enough to reach a conclusion on that. And so we could now explore it with the experiments. Okay, so there's been a lot of previous work trying to measure resistivity in these cold atom systems. but measuring the bulk resistivity has been really elusive in these lattice systems. And I want to show you how we went around doing it. Of course, we can't just measure it, connect leads and measure a current and so on. So we have to be a bit more clever about how to measure resistivity in these cold atom systems. And what we did here is we borrowed a relation from condensed matter. So we have this famous relationship called the Nernst-Einstein relationship. So this tells you that the inverse of the resistivity, which is the conductivity of the system, is the product of two quantities. One of them is the diffusivity. This is a microscopic quantity of the system, how the particles diffuse around. And then there's the compressibility, which is how the particles respond to an external force. So this is how the density depends on the chemical potential, derivative of density with respect to chemical potential. So we're going to measure both of these quantities. And through this Nernst-Einstein relationship, we're going to reconstruct the resistivity. Okay, so let me show you how we do that. So we're going to take a spatial light modulator. So it's essentially like a projector chip, and shine some light on it. And this allows us to pattern a light potential, which we can now project through the microscope onto the atoms and shape their potential landscape. So one thing we did in this study is we wanted to study the system at a fixed doping, because as you remember in the phase diagram, this strange metal only occurred over a range of doping. So we don't want to be studying a very wide range. We just want to fix the doping. And so we want to cancel this harmonic confinement that's coming from the Gaussian laser beams. So we project an extra potential to just make the potential flat over a region of about 30 sites or about 1,000 atoms or so. And then on top of that, we're going to add an extra sinusoidal modulation. So that's what you're seeing here. There's this sinusoidal modulation that basically prepares the atoms in the stripe pattern that you see here. You see this one-dimensional stripe. That's our initial pattern. And then what we're going to do is we're going to suddenly switch off this sinusoidal preparation potential and let the atoms diffuse in the lattice. And by watching their dynamics, we're going to reconstruct the diffusivity, essentially. So here's a picture, at time equals 0, you have these stripes, and then we let the atoms diffuse, and sometime later we just reach equilibrium, and from that we'll extract the diffusivity. So we can fit basically the amplitude of this sinusoid. That's what's shown here. So we start at amplitude 1, and then we watch how the amplitude decays, essentially. And this happens over a very fast time scale of a few tunnelings. We're working at a strong interaction U/T about 8, comparable to what you have in the cuprates. And we're going to fix the doping to about 20%. Again, where this magic point where we have this magic region where you have the strange metal in the cuprates. So that corresponds to a density of about 80%. And what we see depends on the wavelength of the pattern we start with. So if we start with a wavelength of 5 sites, we see the amplitude bounce a little bit. So this is not what you expect from diffusion, right? Diffusion, you just expect an exponential decay of the amplitude. Here, there's a bit of something like a sound mode. If you're like sticking a potential in the gas, then you might expect to excite some sound. And that's what we're seeing here, some damped sound, essentially. And then if we go to a longer wave, this was for a wavelength of 5 sites here. If you go to a wavelength of 10 sites, it's more damped. If you go to a wavelength of 15, it's even more damped, 20, completely damped. So what you're seeing here is an evolution as a function of the wavelength of this pattern from something that looks like a damped sound to more of an exponential decay, which corresponds to what you understand from diffusion. So now we can start making a hydrodynamic model, essentially, of what's going on. So hydrodynamics is basically you write down the conservation laws and some phenomenological equations, and from there you can predict the long wavelength behavior, essentially, of the system. And the hydrodynamics we use is basically 2 equations. One of them is just the simple charge conservation equation. So the rate of change of charge at some point corresponds to the divergence of the current. You have currents flowing into or out of that point. That's the charge conservation. And then the second equation is more of a phenomenological one. So let me first start from diffusion. Diffusion, you might all be familiar with Fick's law from chemistry. if you just have some ink in a solution, it diffuses. That's described by Fick's law. So you have the current proportional to the gradient of the density, with the proportionality constant being the diffusivity. Now, we can't just have Fick's law, because that would just lead to the exponential decay we saw at long wavelengths, but we need to also describe the short wavelength behavior. So we're going to modify this Fick's law. We're going to say that the currents in the system cannot change instantaneously. They have to take some time to build up. And so we're going to introduce a rate of change of the current. And we're going to say that when the current is steady, when this rate of current stops changing, it's zero, then you recover Fick's law. If we set this left-hand side to zero, then you just get Fick's law. But we're going to approach that steady state at some rate, which is given by this gamma here, which is a current relaxation rate. So we have two free parameters essentially in our system, a diffusivity and a current relaxation rate. And if we combine these two equations, we get a second order differential equation, which you're all familiar with. It's just a second order differential equation for a harmonic oscillator, okay, where we're replacing the position with the density essentially. So the damping rate is gamma, and here's where you would normally have omega naught squared, the natural frequency squared. That's just gamma d k squared, where k is the k vector, the wave vector of the modulation we're imprinting. So as you tune the wave vector, you're basically tuning the natural frequency, and so you can go between a regime where you're underdamped to overdamped by tuning this k. And so we can describe this crossover, and we can essentially fit all our data to just these two parameters, gamma and d, and the agreement tells us that this hydrodynamic model makes sense. Okay, so I'll pause maybe here again, since this was a bit more complicated, and ask if you have any questions.
This is very interesting, Waseem. Rene and Luigi have their hands raised, but I think it's just because they didn't unraise them before.
Oh, I didn't, yeah, but I could still ask something, maybe.
All right. Yeah.
So I think I missed this. I missed this wavelength part. So this I think it just went over my head. What is this wavelength again, and how do you control this?
Yeah. So
it's the sinusoidal wavelength which you modulate on top.
Yes, we basically imprint the potential using, so we just have a projector chip essentially. We shine some light on it. We can put any pattern we want, and we can put a sinusoid whose wavelength we can control. Okay. And that, we send this light potential through the objective onto the atoms, and so we can say put a wavelength of 10 sites, prepare the atoms in that configuration, and then remove this potential suddenly and let the atoms diffuse in the lattice.
Mm-hmm. And which parameter then sets if the wavelength? I think you mentioned this also, because you said if you make it bigger. Sorry.
Yeah, it's whatever pattern we put on the projector chip.
Yeah. No. This I understand. I was just, if you go to the next slide, then you see that I think for the short wavelength you could you could see this nice oscillation, but then for the bigger wavelength you couldn't see it anymore. And so, to which parameter of your system do I have to compare the wavelength to understand kind of where
it's a combination of gamma and d, but mostly like if you just had gamma 0, sorry, if you had so like what's controlling is basically the current relaxation. So in order to sort of get this sort of behavior, you want a finite relaxation rate. If the relaxation rate was infinite, then you immediately, your current goes to a steady state, and you just get Fick's law, which at that point you just have diffusion, so you just get the exponential decay. But the fact that there is a finite gamma, that's what gives you the sound.
Okay. And then as you touched on this analogy with a harmonic oscillator, is there any speciality now, because there is now a gamma in front of your N term, which you wouldn't have for a normal harmonic oscillator, right? There, the gamma would only be in front of the first derivative term.
Yeah, I mean, they both enter, so it's
so it doesn't matter quite.
You can't tune purely like one of them. Yeah. I mean, what we're tuning through the k is this omega naught squared essentially. But yeah, it enters in a weird way. Basically, what this combination here, if you want to think about it, like omega naught squared is k squared gamma d. So omega naught is k times square root of gamma d. So square root of gamma d is like a speed of sound, essentially.
Yeah. Okay, cool. Yeah, super.
This is very impressive, Waseem. Really, really impressive results. I need to moderate you, though, and let me tell you, it's going to be 55 minutes already of talking, so we can go for 10 more minutes or wrap it up if you can.
Yeah, sure.
Thank you. This is really, really exciting, very interesting. Thanks.
Okay, so the now what we can do is we can change the temperature of the system and extract this gamma and d versus temperature. I mean, the thing we're really interested in is the diffusivity. So you can see here the diffusivity has some non-trivial behavior with temperature that we've extracted in this experiment by, again, controlled heating of the gas. And then the next part of the story, in order to get the resistivity, remember what we needed: the diffusivity, and we also need the compressibility. So let me explain how you can measure the compressibility in the system, and I'll start wrapping up. So if now we can go back to our original harmonic trap, you remember there the density depended on the spatial position, because in a harmonic trap you have a varying chemical potential, so the density will be smoothly varying. And we can just simply take the derivative of the density with respect to the chemical potential in the harmonic trap, and we can extract the compressibility. And that's what we see here. So these are these red points. We've extracted the compressibility. And the neat thing is, unlike diffusivity, which is a dynamical quantity that's always hard to compute in quantum mechanics dynamics, but here the compressibility is a static quantity. It's just thermodynamics, right? So from there, the thermodynamics is an easy thing to compute in with quantum Monte Carlo, and we can compare that to theory. So that's these green points, and you can see our quantum simulator is doing a great job. So so this way we can extract both the compressibility, diffusivity, both versus temperature, and they're both varying in a non-trivial way, as you see. So now the surprising part comes is when you go and multiply these two things, get the conductivity, take the inverse to get the resistivity, and you see it's a beautiful straight line, okay? So that's indeed what you observe in the cuprates and all these other strongly correlated materials. Here we're reproducing it in this Hubbard model. So we find that the Hubbard model indeed has a strange metal phase. And this is something, it also does violate the MIR limit, which is this dashed line here. This is something we still don't understand the microscopics of, but now we have hope of understanding it, because with this quantum simulator, as you saw in the pictures, we can extract single site quantities. So not only can we go and do something like condensed matter, measure resistivity, we can also go and probe the microscopics and try to understand what's going on. So this is something we're actually doing now, and of course, it's hard to know what to look for in these microscopic pictures. So we're actually borrowing techniques from neural networks, artificial intelligence, to try to look at the picture, to look at the pictures and basically distinguish the strange metal phase from other sorts of phases in the system and see what are the signatures that are there. Okay, so I also want to say that once we did this study, people got really interested in this problem, and there was a lot of numerics that that happened. And of course, since people first started looking at this problem many decades ago, numerics has advanced quite a bit. So now there's more advanced both techniques and also computing power. So here I'm showing some results from our collaborators. This is an exact diagonalization measurement, a calculation that agrees reasonably well with our data. This is exact diagonalization on a very small system. It's just 4x4 sites, and that's really about the state of the art of what you can do with a Fermi-Hubbard system. You can't go much beyond 16 sites. Here's a more approximate theory. This is dynamical mean field theory. And this is an approximate theory that people use often in condensed matter. It works exactly in infinite dimensions, but of course, we're only in 2 dimensions in the system, so you don't expect it to agree well. But now with our quantum simulators, we can start to discriminate between methods that work well and methods that don't work so well. Okay, So I'm going to skip over the next part. I was going to talk a little bit about the pseudogap part, but I'll just skip over it and wrap up. So basically what I've shown you is an exploration a little bit about the different phases of this Fermi-Hubbard model, the Mott Insulator, the Anti-Ferromagnet, the strange metal. And now what we're really pushing towards in the experiments is trying to understand the pseudogap phase, which is basically the precursor to the superconductivity. And maybe we can learn about the pairing glue. And there's, I've shown focused mostly on using condensed matter techniques so far, like things like measuring resistivities. But as I said, these microscopes have been already giving us a lot of microscopic data, and I haven't had a chance to talk too much about that. So with that, I'll just wrap up, and I'll thank the members of my group who have done this work, in particular, Peter Brown and Elmer Guardado Sanchez. And we've had a lot of theory support, in particular from the group of David Hughes at Princeton. And yeah, thank you very much for your attention. Happy to ask more questions.
Thank you very much, Waseem, for the fantastic seminar. Congratulations for the impressive work. It's really amazing. And thank you so much for making it so pedagogical and didactic. It's great that you've gone slowly through many details. I assume that Rene or Luigi may have some question. So please go ahead, Luigi.
Yes, thank you for a beautiful talk. I have many questions. Maybe, by the way, I make a. So Waseem would be happy to meet all of us separately, all PIs. So I think at the end of this, then we can draw an agenda in which we make a separate meeting with him. I think for all technical questions, maybe we can ask in these specific meetings. Okay. I have a couple of questions on the talk. I did not fully understood what. So I think I followed that actually you have kind of oscillations in the density, depending on the say whether you have long or small wavelength. Okay, but then I mean you made the conclusions that actually you found a linear resistivity. So it appeared to me a little bit magic. Can you please comment or elaborate a little bit more on that?
Yeah. So what's maybe confusing is that the data is giving us more than just the DC resistivity. So it's the DC resistivity, the zero frequency, that's the one that has the linear behavior. Okay. And then, but there's really information about the optical conductivity in the system in this data, which I'm kind of glossing over. So what we've done basically is this gamma and the D from this hydrodynamic model, we're kind of backing out the diffusivity, and then through this Nernst-Einstein relationship, combining it with the compressibility to get the DC resistivity. So there's this basically using the hydrodynamic model to get to the DC resistivity. But there's more. I mean, when you're looking at the time, you're also getting information about the optical conductivity, which is not there.
Okay, I see.
A more controlled way maybe to study the optical conductivity would be to do maybe a controlled, like say you stick in some optical potential in your system, and then you start shaking, for example, and you can vary the frequency of the shaking, or you could just take the whole, apply a linear gradient and shake it back and forth on your cloud, and then you can get the conductivity as a frequency.
Okay, I see. Thank you. Say, if I can have a second part of the question. So, as you said, I mean, there were many people try to understand this linear resistance, linear resistivity behavior, or this non-Fermi liquid behavior in strongly interacting, strongly correlated systems. Say, one of the very nice and attracting pictures, attracting from aesthetical point of view, let me say, is based on entanglement. So I think this was the theory of Pierce-Coleman. They said, roughly speaking, that actually in the system, is for some reason that was not understood, or at least was not analyzed, was not clear. Actually, you have kind of separation for length scales, and you have kind of droplets in the system. So at one length scale, in which you have strong entanglement. And then at larger length scale, instead you lose entanglement. So can you anyhow make statements on that? So did you see, or can you measure entanglement at different length scale of the system? Or even strong correlations, So I mean, entanglement is complicated.
Entanglement is always a harder. Yeah, the entanglement is always a harder thing to measure.
It's very complicated. But I mean, let's assume entanglement is distilled of correlation.
Yeah, I mean, microscopes have measured entanglement, but they're very complicated experiments. So there's experiments from Marcus Greiner, maybe you're familiar with, where you prepare 2 copies of the system and essentially do a many-body interferometry.
But it's for the von Neumann entropy. It's a different thing.
Yeah, Ranier, I think. Entropy.
Ranier, yes.
I mean, okay, so I'll say maybe one thing about the linear interior resistivity that we're measuring. So one thing I didn't maybe point out too much because I was rushing near the end is the temperature scale over which we're exploring. So this is 0 to 8T, okay? So in the cuprates, typically, so the lowest temperature point here we're talking about is about 0.3 T, which corresponds to about 1,000 kelvins. So this is really a regime towards the edge of what people measure the linear resistivity in the cuprates. Typically, that's kind of the upper bound of what they measure. And then most of what we measure is at very high temperatures where the cuprates would have already molten already, okay? So there's basically, I would say, 3 regimes of linear resistivity. There's the very low temperature regime where the diffusivity dominates, and the compressibility usually saturates at very low temperatures. And then basically this linear interior resistivity has to be coming from the diffusivity. And then there's the very high temperature regime where the diffusivity saturates and all the linear interior resistivity has to come from the compressibility, which is much better understood because that's purely thermodynamics, and you do expect linear interior resistivity there. And there's an intermediate regime where both quantities are varying, as you saw in our experiment. And again, we're seeing a linear interior resistivity. And maybe there's one line, or maybe there's different linear slopes in these different regions. Yeah, so I think we probably in this experiment exploring a different regime from what the cuprates have, where this theory that you're proposing might be valid. And in these two, the intermediate and low temperature regime, I think are at this point not understood. Only the high temperature regime where it's only coming from the compressibility, that's easy to understand. And then proving it, I think, yeah, the correlations might be what we would have to start looking at to understand.
No, the question is, if you want an extreme simplification summary, is just whether you observe a modulation in space of correlations.
Yeah. I mean, that's what we're trying to do with AI is like we're not sure what to look for. You know, with the anti-ferromagnet, you know what you look at this 2-point spin correlation. That's what you have to look at, right? So this is maybe the challenge that you face. Just like if you have a quantum computer, you can always do the equivalent of numerics. You get the data, but then understanding what is the correct thing to look for, that's the hard part. And that's where we're trying to now use AI techniques to kind of help us know what is it that distinguishes, say, the strange metal or the pseudogap from a Fermi liquid, for example.
I wanted to ask a question. Luigi, can you mute yourself, please? Waseem, this is connected to the question that Luigi was raising about, or that you guys were discussing about measuring entanglement, for instance, right? And then independently of measuring entanglement or any other property of the system. So the basic question I wanted to pose is, what are the measurements that you can do, like at the single particle level? Like, is it possible for you to measure any Pauli direction at the single atom level, or can you say something?
It's not a full quantum computing platform like, say, I mean, like, for example, with Rydberg's, things are much more advanced at this point, but with this sort of system, it's we're dealing with many more particles than than the typical quantum computers that have been built 50. Here we're dealing more with 1,000, but there is still some single site capability, at least in imaging. Definitely in addressing, we can do it. It's just not very high fidelity. Like we can focus the laser beams. We can do any rotation you want locally.
I see.
We can do interference, etc., but they're just much lower fidelity than you would have in a proper quantum computing platform. That's why I'm calling it a quantum simulator than a quantum computer.
Sure.